In 9.9, we're going to seemingly shift gears a little bit and talk about something called power series. But recall in 9.8, we talked about Taylor polynomials and approximating functions using those Taylor polynomials. Well, as it turns out, this topic of power series is going to help us in our journey to try to find the exact value using a Taylor polynomial. And that kind of is addressed here in this title slide you've been seeing here for the entire chapter 9. So kind of just keep that in mind. In 9.8, we talked about Taylor polynomials, which were approximations and they weren't exact. Power series are going to kind of help us build a bridge towards getting to the exact value and something called Taylor series, but that will be covered in 9.10. So power series are just generalizations of infinitely long polynomials. Just like you saw in 9.8, we talked about Taylor polynomials or Maclaurin polynomials. Here, these power series are just a generalization of an infinitely long polynomial. So the general form of a power series that's centered about some point C is given by this form. You'll notice that our summation is going to infinity, unlike our Taylor polynomial that ended at some point, whether it was a 5th degree, 6th degree, 7th degree, whatever the case might be. So this should look a little bit familiar in a sense. Here we have just some general piece, a sub n, and we're multiplying it by x minus c to the n power. So if we kind of expand that out, just like we practiced doing with Taylor polynomials, our first term, if we're starting at 0 here, would be a0. Our next term would be a1 times x minus c to the first power. Our next term would be a2 times x minus c to the second power, and so on. And again, just keep in mind, this is a series, so we're adding up each of these terms, and this dot 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 at the end is implying that we're going out to infinity. So just like you saw with the Taylor polynomial, it will generate a polynomial that's infinitely long. So let's consider a power series, a very basic power series, where c is equal to 0 and a sub n is equal to 1. Well, if a sub n is equal to 1, then there is no term in front of the x parentheses, and if c is 0, then we just have x to the n. So if we kind of practice expanding that out, and it's going to be a good idea to keep on practicing that skill, our first term would be x to the 0 or 1. Our next term would be x to the 1 or just x. Our next term would be x squared, x cubed, x to the 4th, and so on and so forth. And again, we're adding up these terms out to infinity. So you might be recognizing this form. This form follows that form that we know as a geometric series. The reason it follows the form of a geometric series is we see a number, and I suppose it's a 1 if you want to squeeze that in there. It's a 1 times a base to the nth power, and that's a geometric series. So this is a geometric series where our a is 1, again, visible 1 in front of the x to the n, and our r is equal to x. So if we wanted to know what the sum of this was, we could, of course, use our formula that we saw back earlier in chapter 9. I'm going to write this out in word form, and of course the word form of our geometric series formula is the first term over 1 minus the common ratio, and that's assuming r is less than 1. So what would this be equal to in this power series case? Well, our first term is 1, as you can see right here. That's why we have a 1 in the top of this fraction, and then we're supposed to divide by 1 minus the common ratio. R in this case is x, so we're going to divide by 1 minus x. And that's what this power series is equal to. It's a geometric series, and we know it's equal to that because it's a geometric series. So this series will converge to 1 over 1 minus x only when the absolute value of x is less than 1. And again, that just goes back to this idea here. We can only have a converging geometric series if the absolute value of r is less than 1. But we don't know what x is. So this actually produces a range, so to speak, or a window or an interval of possible values for which this infinite series here, or power series, will converge. So just realize that the absolute value of x being less than 1 is really the same thing as saying that our domain or our interval goes from -1 to 1. Those are the allowable x values that would give this geometric series converging to 1 over 1 minus x. So we can actually visualize this with a little number line. For x values in the interval -1 to 1, we know that this series up here, x to the n, will converge. And again, because it's a geometric series. So we've kind of shifted gears a little bit concerning our geometric series, where now we have a variable x in our series. But luckily that doesn't really change much. So this brings up this idea concerning power series and their interval of convergence. It's the interval of x values which lets a power series converge. So when does a power series converge? Well, if it's not an interval, it's going to be the easiest case, I suppose, if you want to think of it that way. Our power series, or our general power series up here at the top, will converge if x is equal to c. The reason it'll converge if x is equal to c is we'd end up with a c minus c here. And for simplicity, or to simplify that notation, we just need to agree that c minus c to the n power is 1, because really it would just converge to the first term, or a0. So kind of a odd way to look at it in a way, because of course c minus c would be 0, but we're just agreeing that of course our power series at the very minimum, if x is equal to c, would converge to just be that first term. And if we're starting at 0, then our first term would be a sub 0. In all other cases, though, we're going to have some sort of interval, like you see here above. A power series will converge anywhere besides at x equals c. And that place, or that interval, we're going to call an interval of convergence, which we'll address in the next slide. Okay, so we define the interval of convergence as the interval on which a power series converges, which then brings up an additional idea of the radius of convergence. And as a visual, it's probably better to kind of see this. So let's pretend that we have this interval of convergence from -1 to 2. And you'll notice we're not including -1 and 2. So we have parentheses here as our visualization. And again, that parentheses we use when we don't have an equal to on our inequalities here. So you'll notice there's a bit of symmetry here. From -1 to 2, the length is 3 units. So if we wanted to look at half of that, then we could say a radius of convergence would be 1.5. Once we kind of realize this idea of an interval of convergence, and then as a little subtopic, its radius of convergence, we need some sort of way to determine how to find this interval of convergence for a power series. And luckily it's going to be the test that was most commonly used in some general regard back earlier in chapter 9, and that was the ratio test. So anytime you see a question asking you to find some sort of interval of convergence, or certainly a radius of convergence, we're going to use the ratio test to determine that. So that's really what the rest of this section is dedicated to, looking at a bunch of examples where we're trying to determine what the radius and maybe the interval of convergence of a power series is. So we're going to go ahead and consider this power series, which you saw from before. We already know the answer to it because it is a geometric series, but for the sake of practicing an easy one first, let's go ahead and verify what we already know from the last slide about this power series. So we're going to go ahead and use the ratio test. As a reminder, the ratio test tells you to take the a sub n plus 1 term and divide it by the a sub n term in absolute value, and we're going to take that limit as n goes to infinity. So our a sub n plus 1 term would be x to the n plus 1 power, and we divide by the original infinite series, which is a sub n, or x to the n power. Here you'll notice we can do a little technique we've been using all throughout this chapter. We can take that power and split it into two bases being multiplied. And the great news about that is we can take those x to the n powers and cancel them, and ultimately we're just taking the limit as n goes to infinity of the absolute value of x. So there's something to realize here. This answer is not infinity. We're not going to take that infinity and plug it in for x and then produce a limit of infinity. The reason we're not going to do that is because there are no n's in what we're taking the limit of. It's almost as if we have a constant of sorts because there are no n's there, and of course n is the thing that's being approaching infinity. So really this is just equal to the absolute value of x, almost again like if it was a constant. So that's our result. Based on the ratio test, we get a result of absolute value of x. And we know by the ratio test that that has to be less than 1. Additionally, we need to keep that absolute value because, of course, x can be negative or positive. There's no information that's telling us that it can't be negative or positive, so we have to keep that absolute value. So again, as a reminder from 9.6, if we do a ratio test on an infinite series, then we're going to say that the result of that limit would have to be less than 1 if our infinite series is going to converge. So that's what we want to do. We want to set the absolute value of x to be less than 1. And again, just as a reminder, like you would have saw in previous math classes, or like you saw in the last slide, setting the absolute value of x less than 1 is essentially the same as saying we have the interval from -1 to 1. So if we want to visualize that a little bit, we can have this visual here of going from -1 to 1. But here's something you're going to have to keep in mind for every one of these types of problems. Not only are we interested in the points between -1 and 1, we're also interested in -1 and 1 themselves. We're going to have to always check the endpoints to see if those also produce a converging value. So if they do, we can include them in our answer. So let's go ahead and check the endpoints. Luckily, to do this checking of the endpoints, all you're going to have to do is take the two endpoints of -1 and 1 and plug them back in to your original infinite series to see what happens. And you'll notice when we plug in x equals 1, we'll have 1 to the n power, and of course that would just be 1 plus 1 plus 1 plus 1 to infinity. And we know that series would, of course, diverge. If we plug in -1, we'll end up with -1 to the n, and hopefully you recognize that as an alternating series. Of course, an alternating series does not converge, so both of these endpoints produce something that diverges. Because of that, we don't want to include the endpoints in our answer. So we're going to go ahead and put these parentheses here as a visual, and of course we can say that our radius is 1, and to finalize this answer, we can just go ahead and write this out in word form. The radius of convergence is 1, and the interval of convergence is -1 to 1, but we're not including the endpoints of -1 and 1. Okay, so just like I said in the last slide, really the rest of these slides are just examples of these power series where we're checking to find the interval of convergence and the radius of convergence. So here we have an infinite series of x to the n over n factorial, and we want to find the radius and interval of convergence, which means we need to use the ratio test. If we apply the ratio test, we'll end up with x to the n plus 1 power over n plus 1 all factorial. Again, don't forget to use n plus 1 with parentheses when you plug it in. And we'll divide that by the original infinite series x to the n over n factorial. Every one of these problems is going to require that you take that bottom fraction and multiply by the reciprocal. We can't take off that absolute value, so we're also going to keep that there. Okay, so there's really nothing too special about these problems considering you had a lot of practice with 9.6. If you want to simplify this, there are two things we can do. We can take this x to the n plus 1 and split it into two bases of x being multiplied. In the bottom of the fraction, we can take the n plus 1 factorial and expand it one step to n factorial. The reason we would want to stop there is so the n factorial in the top and the bottom cancel, and of course you can see the x to the n in the top and the bottom cancel, and we're just left with x over n plus 1 in absolute value. So we have two separate things here. We have a variable x, and then we have our n as it's going to infinity. A good idea usually is to just split those into two separate things, just so we don't kind of confuse everything that's happening here. The only thing affected by the limit, because n is going to infinity, is the piece that contains the n. Everything else, which is the x in this case, is basically seen as a constant of sorts, because there are no n's in that piece. So you don't always have to do this, but for the sake of these examples, I'm going to go ahead and pull that absolute value of x to the front of the limit, just so we don't misinterpret that x being present there. So if we just focus on the limit for a moment, that's a very basic limit. If we take that limit as n goes to infinity, we'll end up with 0. And of course, 0 times absolute value of x is just 0. So don't kind of lose sight of what we were doing from the very beginning. After all of these steps, we found a result of 0. And by the ratio test, if our infinite series is going to converge, we have to set that result to be less than 1. And luckily, 0 is always less than 1. That is true for all x values. So then how do we come to a conclusion for our interval of convergence? Well, if this is true for all x values, then our interval of convergence would be negative infinity to infinity. And in that particular case, our radius of convergence would just be infinity. Okay, another illustration of testing a power series to determine its interval of convergence and radius of convergence. Anytime that subject comes up, just as your standard process that you're going to have to apply, we're always going to use the ratio test. And here you can see this is going to produce a really big kind of ugly fraction, but luckily if you just break down the pieces, it's not too bad. We'll have x to the n plus 1 over n plus 1 in parentheses, keep that in mind, times 5 to the n plus 1, all divided by our original series, x to the n divided by n times 5 to the n. Every one of these problems will always have the same first step in terms of the setup, and then the same second step in terms of you taking that denominator and multiplying by the reciprocal. After that, just keep in mind we got to keep the absolute value, especially because of the presence of x, which could be possibly negative. Okay, so to simplify this, there are no factorials. In the top and the bottom, I see a power with a plus in it, so I can split that into two bases being multiplied. And you'll notice when we split the top and the bottom with the x to the n plus 1 and the 5 to the n plus 1, we'll get four things to cancel. The x to the n in the top and the bottom, and the 5 to the n in the top and the bottom, which leaves us a result of n times x divided by 5 over n plus 1. So keep in mind, we're only interested in taking the limit of the stuff that has n's in it. Everything else we kind of view as a constant of sorts because it's not being affected by that limit. So I'm going to go ahead and again pull off that absolute value of x and go ahead and pull that to the front. Just again as a clear step showing that we realize that that x is not being affected by the limit. After that, it's just a matter of taking this limit. You'll notice in the top and the bottom we have a power of n to the first power, I should say. Those essentially cancel out in infinity, and we're left with the value of 1/5. So the result of our ratio test is absolute value of x times 1/5. And if this infinite series up here, our original problem, if that's going to converge, our result has to be less than 1. So this is very similar to the couple of problems you've seen before, except we have a 1/5 in the front, so of course we can multiply the 5 to the other side. And if the absolute value of x being less than 1 produces an interval from -1 to 1, then of course the absolute value of x being less than 5 would produce an interval from -5 to 5. Don't make the kind of common mistake of just kind of being happy after all of that work and just saying that's the answer. Don't forget, we also need to check our endpoints. So again, we're going to draw a little visual of this so we can kind of see what's going on. So we don't really have a complete picture yet. All we know is that our interval goes from -5 to 5, and we need to check to see if -5 or 5 could also be included in this answer. To do this, we need to take each of those endpoints and plug them in to our original infinite series, or the original problem, and then see what's happening with that result. When we plug in 5, we'll have 5 to the n over n times 5 to the n. And of course, we can simplify that to be just 1 over n. And that we don't need any special test or anything to do. We know that's a harmonic series. And of course, that diverges. So we're not going to include the endpoint of 5. What happens when we look at -5? If we plug in -5, we'll have -5 all to the n. Careful with the way you plug that in. It would be all to the n power over n times 5 to the n. And just realize we can apply, I don't want to call it a trick, but certainly something you might not realize. -5 is really -1 times 5, of course. And all of that is to the n power. Anytime you have factors or things being multiplied to a power, each of those gets that power. And of course, we want to apply that property here so that we can see that the 5 to the n's would cancel each other out. And then we're left with the infinite series, -1 all to the n power divided by n. And again, if you have that basic knowledge of very special series that we're supposed to know, this is our alternating harmonic series, which converges. I'm just adding this little bit of extra information here that it converges conditionally. But bottom line is, all we really care is that it converges. That's the thing that really is what we're interested in. And because of that, that means we can put a bracket as our visualization up here. We can put a bracket on that -5 because we can include that endpoint. With +5, we can't include it, so we're going to put a parentheses. And to just paint a very clear picture of what's going on with our number line here, anything to the left of -5 and to the right of 5 will be diverging. Anytime we have any x value pertaining to this infinite series that's either less than -5 or bigger than 5, our infinite series would not converge. But if we had any value in between -5 and 5, our infinite series up here would converge. And I guess there's one other thing we can mention. Additionally, at -5, it would also converge based on this little thing we did below where we check the endpoints. After that whole story has been told, so to speak, we can finalize this answer now. We can say that our interval of convergence is from -5 to 5, including -5, so we have to put a less than or equal to. And then, of course, you can see visually here that our radius of convergence is 5. Okay, another example of power series and determining the radius and interval of convergence. As soon as you see that question come up, apply the ratio test. Here, I guess the one unique thing as compared to the previous examples is we don't have a fraction here in our infinite series. So we don't have to worry about the whole multiplying by the reciprocal. We can just go ahead and look at what we have after we set up the ratio test. And again, be very careful. Every time you plug in that n plus 1, plug it in parentheses. So we have n plus 1 all to the n plus 1 times x minus 1 all to the n plus 1. And then we divide by our original infinite series, n to the n times x minus 1 to the n. Okay, so like you've kind of gotten accustomed to in a lot of these problems, we're going to take some stuff and split it. But before we do that, because of the kind of mess that's going to be produced when we do that, I'm going to go ahead and split off the n's altogether and the x's altogether. If we do that, we'll end up with n plus 1 to the n plus 1 over n to the n, and then we'll end up with all of our x terms all collected in this other fraction. I'm just doing this just for the ease of kind of looking at this as not one big problem, but really the n's versus the x's. Okay, once we do that, we can go ahead and start making some cancellations. I'm going to go ahead and cancel the x minus 1 to the n power over x minus 1 to the n power. Again, we split this piece up using that property of exponents. And I went ahead and left the numerator with the n not split up, and you'll kind of see why in a second. So we end up with x minus 1 in absolute value. Of course, the n fraction doesn't need the absolute value because that'll always be positive as n goes to infinity. Okay, we're going to go ahead and pull out that x minus 1 to the front, and now I'm going to go ahead and split this up. The n plus 1 to the n plus 1, of course, can be rewritten as n plus 1 all to the first power and n plus 1 all to the n power. So how are we going to take this limit? You might be tempted to say something like infinity times infinity to the infinity over maybe an infinity to an infinity. Unfortunately, none of that is equal to infinity. It could be equal to infinity, but that just is kind of a mess that doesn't really make much sense. So how are we going to approach this limit? Well, what we're going to do is take these two pieces that have an n power and combine them into one fraction as n plus 1 over n, all to the n power. I suppose a very important question would be, why are we approaching this problem that way? Well, if you recall earlier in this chapter, we went over a very special limit, and that special limit was given from this form. And if you recall, that was equal to e. It appeared in another form as a split up fraction, or splitting up the fraction, but either way, both of these limits produce a special value, and that of course is our exponential number e. So as it turns out, when we take this limit, all of that piece is just e. Now I guess fundamentally, that really didn't matter too much, because bottom line is, when we plug in infinity for n plus 1, that's infinity times e is of course infinity. And then if we apply that infinity in terms of multiplication to the x minus 1, we're still going to end up with infinity. So that's the result of our ratio test. If we want to check for convergence, our result has to, of course, be less than 1. And as we all can appreciate very easily, infinity is certainly not less than 1. It's absolutely never true. You can't play with infinity that way, as this little cartoon character just discovered. So since that is never true, do we actually have some sort of convergence going on here? Well, if you recall from the first slide, if we don't have an interval of convergence, there's possibly a point of convergence. So here's the question we're trying to figure out. Are there any values of x that will make this series converge? And there is one value of x that will make this series converge. And if you again refer to that first slide, when your x value is equal to c, and by the way our c here is that 1, then we can get our infinite series to converge at least at that point. So for x equals 1, this series will converge. And I suppose we can try to visualize that, even though it's kind of odd to try to visualize a single point as being an interval of convergence. But as it turns out, our interval of convergence is the point x equals 1. And again, since there's no space we're covering from one number to another number, that would produce a radius of convergence of 0. So again, just keep in mind that this problem is illustrating the other type of convergence where it's at a point and not an interval. And that'll happen anytime that you get these answers of infinity after you do the ratio test. Okay, here we have another power series that we're testing for its interval of convergence. So we're going to go ahead and apply the ratio test, and this might be the ugliest one yet that we've seen. But again, just manage those pieces of this ratio test very carefully, and it shouldn't be too difficult to at least set up. So again, the first step is to always take the n plus 1 and plug it in for n, and then divide by the original infinite series. The second step will always be taking that denominator and multiplying by the reciprocal. Here, we've got to realize that, and I guess we could have seen that at the beginning here, our power series has an alternating portion to it. So after we set up this ratio test, if we apply these absolute values, you'll notice that the absolute values would cancel the alternating parts, and there's two of them. In the top we have a negative 1 to the n plus 1, and in the bottom we have a negative 1 to the n. Both of those components are producing negative values because they're alternating. So if we apply the absolute value to those pieces, they disappear. And of course, we're left with this result. Again, like you saw in the last slide, I'm going to go ahead and split off the n fraction together with the x fraction together. After that, we can, of course, in the x fraction, split up the power. And of course, because of that, cancel the x to the n power. After that, we're left with the absolute value of x, and then I'm going to go ahead and change those square roots over to powers. We, of course, want to view these things as powers, so it's a good idea to change those over to a 1/2 power. As it turns out, if you take this limit to infinity, the biggest power of n you see in the top is a 1/2 power, the biggest power of n you see in the bottom is a 1/2 power, and of course that would simplify to be a 1, and when we take that limit, we're just left with the absolute value of x. And like you've seen in a couple examples here in this lesson, if we set the absolute value of x to be less than 1, because we know the ratio test tells us we have a converging infinite series if that's true, then we can realize that the interval of convergence here is negative 1 to 1. But again, don't make the mistake of forgetting to check the endpoints. And here is where it's going to get really involved. I'm not sure you might have contemplated this question, but is it possible to end up with having to do some sort of other test as you test the endpoints? And maybe we'll discover that that can happen here. So let's go ahead and take our two endpoints and plug them in. I'm going to first start with positive 1. If we take that positive 1 and plug it in, we'll have 1 to the n power, and luckily that is just 1. So we're just left with negative 1 to the n over the square root of n. In all the previous examples, we were able to look at this resulting infinite series and quickly determine if it converged or diverged without having to do some sort of extra test to determine that. Well, in this case, we don't really know what's happening here until we apply a test to determine the convergence. And you'll notice we have an alternating series, so we're going to have to do the alternating series test. Luckily, at this point, we can kind of simplify the steps of the alternating series test and just keep them very simple and straightforward. Are the terms positive? Yes. Are the terms decreasing? Yes. And of course, we're looking at the non-alternating part as we're contemplating these three checks. So will the limit of 1 over the square root of n produce a 0? And again, the answer is yes. So we know that this infinite series here is converging by the alternating series test. And again, it's always important to state what test you're applying, and of course the conclusion that it's giving you. In this case, the infinite series converges. If we kind of take all that and apply it to this problem, we know we can include the value of 1 in our interval of convergence. But before we move on to that final answer, we need to check negative 1. If we plug in negative 1 in our infinite series, we'll end up with negative 1 to the n times negative 1 to the n. And of course, if we multiply two bases that are the same, we add the powers. N plus n is 2n. Okay, so you might be tempted to look at this and go, hey, it's kind of like what we saw above. Negative 1 to the n was alternating, so negative 1 to the 2n must also be alternating. Well, we haven't really seen this before, but really think about what negative 1 to the 2n would produce. If we plug in 1, we'll have negative 1 squared, or positive 1. If we plug in 2, we'll have negative 1 to the 4th, which is also positive 1. If we plug in 3, 4, 5, and so on, and you can do this on the side if you want to prove it to yourself, but for every n you plug in, you'll have negative 1 to an even power. And as we all know, a negative number to an even power will always be positive. So as it turns out, negative 1 to the 2n will always just be a positive 1 power. So luckily here, we're left with an infinite series that doesn't need a special test to determine convergence. We know that this infinite series is a p-series, where p is equal to 0.5, which is less than 1. And if you recall, anytime that happens, our infinite series, or p-series, diverges. Okay, after all of that side work, we're now finally ready to finalize this answer and write out the interval of convergence. The interval of convergence goes from -1 to 1, and we're going to include 1, so we're going to have to put less than or equal to there. And then, of course, we can see a radius of convergence would be from 0 to 1 or -1 to 0, which is a length of 1, so our radius of convergence is 1. Okay, so in this last example, we have an AP test question where I've spread out the answer choices of A through E, and it's a very simple instruction here. Which of the following series converge for all real numbers of x? And you'll notice all of these are power series. They all have an x in them, so these are all power series. So to determine whether these converge or where these series converge, we're going to have to apply the ratio test. But that's a lot of work. If you're critical in terms of the way you think about these answer choices, maybe we actually don't have to do that much work to at least start eliminating some answer choices. And you'll notice A, B, and C might fall into a category of infinite series where we don't really need to do much to determine whether they converge or diverge. And you'll notice this. The top of all of these fractions for A, B, and C all grow way faster than the bottom. X to the n power is much bigger than just an n. And to think about that, pretend you plugged in an n value of 2. X squared as compared to the number 2 is of course much bigger. If you think about plugging in an n in the choice B, you'd have maybe x squared over 4, which is again much bigger than the bottom. And same for choice C. If you just chose a random number for n and plugged it in, like a 2, you'd have x squared over the square root of 2, and of course the top is growing way faster than the bottom. Anytime that happens, in terms of taking a limit of that infinite series, we of course would get a value of infinity. If the top of a fraction is growing faster than the bottom, as we take that limit to infinity, the result is of course infinity, and because of that, we would never say converging in those cases. So we can say at least real quickly that A, B, and C all diverge. Can we maybe apply this reasoning here to either choice D or E? I'm going to leave D alone for a second and give you this little fact here. Factorials, which are in the top of this fraction, grow much faster than exponentials, which are in the bottom of this fraction. And again, to prove it, you might want to do this on the side or with a calculator just so you can see it. But if we chose a number for n, and I'm just going to pick maybe 5, we'd end up with 5 factorial times x to the 5th power over e to the 5th power. Now, e to the 5th power can get pretty big fast, but if you compare that to the numerator is getting bigger much faster. So as it turns out, choice E is kind of out of the discussion here, since the numerator grows faster than the denominator. Once we take that limit, we can of course see it's equal to infinity. So I guess this is an interesting question where if you just kind of knew that one fact about fractions going to infinity, we could kind of just get the right answer by process of elimination. But for the sake of practicing this one more time before we close off 9.9, we're going to go ahead and show why D is the right answer. To show why D is the right answer, we need to, of course, apply the ratio test. This power series, if it's going to have an interval of convergence, would be determined, of course, by our ratio test. So let's go ahead and apply the ratio test. And here I'm going to go ahead and skip the step, mainly for space reasons. But I think once you get the hang of this, you can skip that step. I'm going to skip the step where I set up the a sub n plus 1 over a sub n fraction and jump straight to multiplying by the reciprocal of the denominator. So we're going to take n plus 1 and plug it in every place we see n, and then we're going to multiply by the reciprocal of the denominator, which I'm not writing, which would just be the reciprocal of our infinite series, n factorial over e to the n times x to the n. Okay, so there's a lot we can simplify here. We can split up the power on the e, so it's e to the n times e to the 1. We can split up the power on the x, that's x to the n times x to the 1. And we can take our factorial here in the bottom, n plus 1 factorial, and expand it one step so that it's n plus 1 times n factorial, and you'll notice a lot of stuff cancels. Ultimately, we're left with e over n plus 1 times the absolute value of x. And if we plug in infinity, you'll notice that all of that becomes 0, and of course 0 times anything is 0. By the ratio test, our result has to be less than 1, and of course 0 is always less than 1, so we can come to the conclusion that that is always true for all x values. So we can say our interval of convergence is from negative infinity to infinity, or if you go up here to the original statement in the problem, we wanted to find the answer that converges for all real numbers of x. And of course, another way of saying that is negative infinity to infinity, or again, all real numbers.